Okay, good morning, everyone. So we will start the webinar from now. So firstly, I would like to introduce about the VPEC. So VPEC is Vietnamese Power Electronics Committee. So every month we organize a webinar. So every people in power electronics area and some other related area can connect and talk and discuss together. So today we have two presenters. One is Japanese and one is Vietnamese. So firstly is Dr. Yoshikazu Kuwabara. So everyone can call him like Kuwabara. He graduates my doctor degree in my laboratory, in same my laboratory. So he in Japanese, so we call he like my senior, my senpai. So today we are very happy to have his presentation. It's a very new topic and very interesting topic. Uh, uh, During his doctor course. So firstly, I would like to Kuwabara-san can have the introduce about himself. Hello, Kuwabara.
Hello.
Yeah. Can you turn on the screen, the webcam so everyone can see you?
Yes.
Okay.
Can you see me?
Yeah, I can see you in your home, Japanese traditional home, right?
Oh, a little bit messy, so don't care about the backside. So
Yeah.
nice to meet you.
Yeah, nice to meet you. So can you have the short introduce about yourself and then we can start the webinar. Yeah.
Yes. Maybe I want to use a slide. So can I share my screen?
Yes. So firstly, I will turn off my sharing. Yeah. Okay. So can you please share your screen?
Okay.
Yeah, I can see the first slide. Yeah.
First slide. So yes. So before, nice to meet you, everyone. My name is Yoshikazu Kuwabara. I'm from Tokyo Metropolitan University. And today I would like to talk my research. The title is Design and Implementation of the Current Sensor using Aircraft Coil for Integrated Power Converter Circuit. And before my presentation, I will introduce myself. So, can you see slide 2?
Yes, I can see now.
Okay. So, my name is Yoshikazu Kawabara, and I was born in the October 3rd, 1991, and I majored electrical engineering, and I was belonging to the power electronics laboratory in the Tokyo Metropolitan University, and I entered that university master course from 2015, and also I start the PhD course 2017, and just last week I graduated this university, and I will start. I will start to work in the Nissan, which is a Japanese car company. Actually, 3 days later, I will start to work. And okay, I just also explain my university. My university, of course, placed in the Tokyo, and this is a Tokyo. And yes, my university placed in the west side of Tokyo. Here, and this picture shows our laboratory seminar camp. every year, our laboratory held this kind of seminar camp, and our laboratory member and graduated member attended this seminar camp and discussed about research and chatting in this seminar camp. And this picture shows Tokyo Metropolitan University. So, okay, so finish my self-introduction. So let's move on to my research. Now, okay, so today I will talk about my research background and the purpose of my research. And to achieve this purpose, I propose the current sensor, which called the integrated air core coil. And then I will measure the switching current using this current sensor. Then conclusion. So let's move on to the research background. Can you see page 4?
Yes, I can see page 4 now.
Okay, so as we know, the power converter circuit is one of the main topic in the power electronics, and the power converter circuit converts electrical energy to adaptive energy for each application. So this figure shows the application of power converter circuit, and as we can see, the power converter circuit applied a lot of applications. And the demand of this power converter circuit is downsizing and high efficiency and high reliability. And to achieving these demands, recently the power devices, the performance is very improved because such as silicon carbide and gallium nitride. And thanks to this improvement, the power converter circuit can operate high speed and fast switching. And this operation enable this kind of passive component to be downsizing, and also this circuit enable the wire to be laminated, as shown this picture. So downsizing and laminated enable more compacted integrated power converter circuit. On page 6, and on the other hand, to achieve the high reliability, sensors are playing an important role. Sensors' role in power converter circuit are monitoring and observing the circuit operation and condition at online or offline. Mainly, there's 3 types of sensors mainly used in the power converter circuit: voltage sensor and current sensor and thermal sensor. And of course, these sensors should be improved for the integrated power converter circuit. And in this research, my research focusing on the current sensor. So I will talk more detail about the current sensor. So now it's page 8, and in the power converter circuit, these kind of current sensors are used for each applications. And as we can see, these current sensor has each characteristics as shown this part. So for example, if we want to measure the switching current for loss calculation, we should choose a wideband with current sensor, like like this current sensor. On the other example, if we want to measure the DC current, we have to choose the current sensor which can measure the DC current. So in this case, this current sensor or these current sensors. So from this figure, we can say each current sensor has disadvantage and advantages. So we should use each current sensor for suitable applications. And also the connection types and the size of a current sensor must be also considered to use the current sensor. And the current sensor, the connection type of current sensor usually 4 types, insert type and mount type or clamp type or through-hole type. And insert type of current sensor is such as a shunt resistor is applied by cutting the wire and insert it. And the mount type of current sensors such as magnet resistor is applied near or on the wire. And the clamp type of the current sensor, such as Rogowski coil or current transformer, is applied by the clamping the wire, as shown on this figure. And through-hole type of current sensor, such as hole sensor. In this case, the wire must be through the hole, like this. So if connection type or the size is not suitable for the wire geometry, insertion wire must be connected. So this slide explains about what is the problem in the of the insertion wire. If so, for example, if we want to measure the switching current which flows in these kind of power devices, we need a wide bandwidth current sensor, and those current sensor structure is like normally this structure. However, we cannot apply this kind of current sensor directly to the power devices because this current sensor, how to say, there is no space to apply the current sensor to the power device. So therefore, insertion wire must be connected, as shown in this figure. And this insertion wire is affected to the switching current. This figure shows the switching waveforms with and without the insertion wire at turn off. Black waveforms shows switching waveforms with insertion wire, and red waveforms shows switching voltage without insertion wire. So as we can see, the switching waveform is totally changing. So, you know, of course, the accurate waveform is always desired to evaluate accurate evaluation. But the current waveform changing after insertion wire is connected easily. And on the other hand, the wire in the power converter circuit is laminated for improving the circuit performance and downsizing the circuit. And laminated bus bar is one of the most widely used in the laminated wire in the power converter circuit. And this figure shows the basic structure of the laminated bus bar. This structure is so simple. Plus and minus bus bar is placed closely through the insulators. And the laminated bus bar usually connect the DC capacitor and power devices, as shown in this figure. So, and we can see conventional current sensor cannot be applied in this kind of laminated bus bar without insertion wire. So, and recent research, many research has been discussed to improve the conventional current sensor, and those current sensor can reduce the insertion wire, but there is no research of current sensor for laminated wire. And I can ask to everyone how to connect the current sensor to this kind of wire. So, and this is the main issue. No current sensor is for laminated wire. So, objective of my research is proposing the current sensor for laminated wire. And this time, the research target is laminated bus bar, and the current sensor for laminated bus bar is proposed in this research, and also what it can do by measuring the bus bar current is considered. And in the laminated bus bar is applied this part, and the target current is here, this current. So, and then I will explain the proposed current sensor. And page 15, and integrated air core coil is proposed as a current sensor for the laminated bus bar. And this figure shows the structure of integrated air core coil. And this current sensor consists 3 layers. Top and the bottom layer is a conductor, so bus bar. And the middle layer is insulators. And the thin air core coil is inserted in these middle layers. And the shape of the air core coil is rectangular. And the bus bar current is measured based on the coil voltage, as shown this equation. And also the equivalent circuit of current sensor is considered. And this figure shows the straight components of the current sensor. And this figure shows the equivalent circuit of the current sensor. And in this time, the bus bar capacitance is considered to the dominant value with other capacitance. Therefore, bus bar capacitance is included in the equivalent circuit. And to measure the bus bar current, we should take care of this component. And based on this, so page 16. Based on this equivalent circuit, the post-processing method to obtain the bus bar current is considered. And based on that equivalent circuit, the transfer function is obtained as shown this top equation. And from K1 to K4 is a coefficient, and that coefficient consists each straight component. And from this transfer function, the bus bar current can be shown this equation, and we can obtain the post-processing method by applying the inverse Laplace transform. And this is a post-processing method. So using this post-processing method, the switching current is measured. And this is page 19. And switching current is evaluated, and this time the experimental condition is as shown this table, and using the double pulse test is conducted using the back chopper circuit as shown this figure. And the right side figure shows a prototype of the back converter circuit, back chopper circuit with current sensor. And the integrated air core coil is placed this part. And this time the geometry of air core coil is determined as shown this this parameter. And I measure the busbar current. And this is a measurement result. Left side figure shows coil voltage, and the right side figure shows a busbar current. So firstly, the coil voltage. This coil voltage measured by the measurement equipment, and based on this waveform, the post-processing method is applied to the coil voltage, and we can get the busbar current as shown this figure. And this time the switching waveform has a resonance component of 76 megahertz. And from this experimental result, the current sensor can measure the switching current using the post-processing method. It is confirmed. Okay. So finally, the conclusion. Firstly, I introduced the research background, and laminated busbar has been applied in many power converter circuit, and conventional current sensor has not applied in the laminated busbar. Therefore, integrated air core coil is proposed as a current sensor. This current sensor is suitable for the laminated busbar. And also to obtain the busbar current, post-processing method is considered based on the equivalent circuit. And it is confirmed that the current sensor can measure the switching current without the insertion wire. So finally, in my doctoral thesis, the new current sensor suitable for the laminated wire is established. Okay, so thank you for your kind attention. So, Kaman ka banzanyo is. I want to say the thank you very much in the Vietnamese. So thank you.
Yeah, thank you very much for the presentation. It's very interesting. Even me, I listen maybe second time because the last time I attend your doctor defense, but
Yes.
still I can get many new interesting knowledge.
Yes.
Yeah. So first, now some people want to have the question. So I will ask. Firstly, is
Yes.
Dr. Ding in Toyota? So can you make your question?
Hello. Do you hear me?
Yes.
Yeah.
Okay, nice to meet you. This is
Nice to
Ding
meet you.
from Toyota Institute, IT Institute of Technology in IT.
Yes.
Thank you very much for your very kind presentations. And I got some questions. First one, regarding the technique, you measure the coil voltage? right?
Sorry, say it again. I measured.
So you measure the coil voltage
Yes, yes,
to determine the current, right?
yes.
So my question is, how big of the voltage signal, like in the order of nanovolt or microvolt or millivolt? So how large of the signal?
Uh, this time coil voltage this one.
Hmm.
So around 15 volt.
Oh, really? That's
Yes,
big.
yes. Because the this coil voltage decided by mutual inductance and DIDT of the busbar current.
Hmm.
And this time the mutual inductance is set to the very big value. That's why I got very high voltage.
Mm, but this high voltage may be because as I see in your figure, the voltage is very big at
Yes.
first, but in some steps later, it becomes very small. Then how do you determine which pulse, which is the significant value, or how to say? How do you do your post processing?
My post processing.
Mm-hmm.
Now I calculate by myself, and I didn't make any electronic circuit yet. So if we want to measure the accurate switching waveform using this post processing method,
Mm-hmm.
we should calculate it by myself.
Ah, so you do it, I mean, post processing offline or online?
Offline.
Ah, okay, I understood. Means you use oscilloscope to measure the waveform, then you export the waveform into like Excel or other
Yes, yes,
software,
right,
then you
right.
calculate by hand.
Yes,
Ah,
because
okay.
if we want to measure switching waveform for calculate loss calculation, we don't need to calculate. Sometimes we don't need to calculate online.
Mm-hmm.
But depends on application.
Sure, but I think in term of measurement, we may need to measure for like to control or for protection, right?
Yes, yes.
Hmm. So, what is the application of offline measuring and calculation? Could you share some ideas?
And if
Application.
okay, and this post processing method is for the accurate switching waveform. That means we if we don't want to reduce this resonance components, we should use this post processing. But if we want to know the just want to get the amplitude of the current, we just can use simple simple calculation post processing, like use based on this equation.
Mm-hmm.
And
Okay.
also
Actually,
yes.
I will please go ahead.
Okay. And also, in my doctor thesis, I also consider the overcurrent detection method
Mm-hmm.
using the this coil voltage directly.
Mm-hmm. Okay, but as I said before, that is you done using the offline method, means it has no effect on the control or protection online, right?
Yes, and maybe if we want to use off online, I should we should consider the how to implement this method to
Mm.
the offline or online method.
Yes, that is the my next question. So, have you ever been thinking about the implementation of post processing, like analog approach or digital approach?
Actually, not yet.
Because I think it is very, very difficult. Because in your post-processing equation, I see
Yes.
some differential
Yes.
factors.
Yeah.
Even second order,
Yes.
first order and second order, it will be very difficult to implement, right?
Yes. Yes. Right.
Okay. Okay, so let's talk about the design. So in your equation, the voltage depends on the M. You said
Ye-
that is a mutual inductance, right?
Yes.
So the question is, how do you design M?
Yes. So this M decided by the structure of bus bar length. Actually, this part. Can you see? And also the cross section area of the current air core coil. So that means this area.
Mm-hmm.
So I think the laminated bus bar length cannot change for the current sensor. So if we want to design the mutual inductance, we should design this coil structure.
So how do you decide the number of turns, or like the MLT, the mean length turn, or something like that? Or even continue.
We can design based on the how to say we can design the mutual inductance based on firstly the DIDT of the current. Maybe we can estimate DIDT based on the data sheet of the power devices. And also the coil voltage is we can determine by myself. This coil voltage depends on the measurement tool. So the value, mutual inductance value is decided in this case. And sorry, and I couldn't understand so much the mutual. How you said how do you design mutual inductance value?
My question is, how do you design your sensor? Then, because your sensor relies on M, the mutual inductance, and you said
Yes.
that M depends on the shape of the bar and
Yes.
the number of turns and the cross section area.
Yes.
Then you said that among those parameters, the number of turns is
Yes.
the most important, right?
That is depend. The number of turn and this cross section area also can change. So we can decide the turn number and cross section area by myself.
Do you have any like step-by-step design guidance?
Yes, actually yes, but now I don't have maybe slide. And actually, that method discuss about this paper.
Oh.
And we published this year, I think. So maybe you can check how to design this coil.
Okay, I will check later.
Yes, so sorry for that.
Yeah, no problem. Okay, my last question, because some others also want to ask you. My last question, in terms of hardware implementation, so how do you insert the insulation between the top layer and bottom layer? Or do you use a multi-layer PCB or something like that?
Now I designed using the 3 PCB. So
3 layers or 3 individual PCB attached together?
This time 3 layers. PCB.
Uh-huh. 3 layers? I think it should be 4.
Maybe, okay, insulators layers, yeah, 2. So actually, yeah, 4 layers.
Okay, that is
Yes.
4 layers, I think.
Yes, okay.
Mm-hmm. Okay, so that is all of my questions. Thank you very much.
Thank you.
Thank you very much for your question and discussion. And Dr. Thuận in UT Dallas also have a question, but maybe a little bit similar with Dr. Ding already much. But could you please talk something if you want to have more detailed question?
Hello, this is
Hello.
Thuận from University of Texas at Dallas, USA. So thank you for your presentation. So yeah, my question is many things that I want to ask already you already answer from question of Dr. Ding.
Yes.
So but my last question is, do you use any FEA simulation tool for the coil design, and how you can accurate measure the mature inductance and like trace inductance or trace capacitance in your system? Yeah, could you please talk about that? Thank you.
Okay. Thank you for your question. Firstly, I to obtain the inductance parameter, I use electrical magnetic simulation. Like, okay, I use this electromagnetic simulation software, and I calculated using I modeling the coil structure and the bus bar, and then I can obtain the 3 inductance. And the capacitance, in the capacitance is I just calculated the basic equation, capacitance basic equation, like the area and the length of the each conductor. You know, so you can you understand that?
Yeah, I can understand your explanation. So, did you verify with the measurement of the charge inductance and capacitance by a machine like impedance analyzer? And
Okay, yes, and after got that value, I measure that value using prototype and time domain reflectometry.
what is that? The last one.
Time domain reflectometry
Okay.
is a measurement method.
Okay. Thank you.
Yes.
Yes, thank you very much for your discussion. And any people have any other question? Some people are typing, but I have a question for speaker. So thank you, Kuwabara, for your presentation.
Yes.
I just concerned like why the shape of the coil is rectangular. What is the advantage of rectangular, or do you think about other shape?
This time the rectangular, I just consider rectangular shape, and because we should insert the coil inside the laminated bus bar. That means we cannot use to say circle shape coil because laminated bus bar want to reduce the thickness. So that's why I choose a rectangular shape this time.
Yes, I understand. Thank you very much. And I have other question because no one have the question now.
Okay.
So my question is, why in the your prototype the coil have the 20 turn, right?
Yes. Yes.
So why do you decide that is a 20? Is what is advantage here?
This is as I said, depends on the DIDT of the busbar current and the coil voltage. And this time, why I decide to 20 turns is I want to get a high, maybe larger voltage around the 20 volt, and also the DIDT. We can expect the DIDT is this time maybe 1.5 ampere per nanosec, and I calculated the mutual inductance based on that limitation, and then I decided 20 turns this time.
Yes, thank you very much. So let's come back. Is there any other people have question? Yes, Dr. Ding still have some questions. So do you have time for maybe some minutes? So someone still have some question?
Yes, yes.
Yes, Dr. Ding, can you turn on and talk your question?
Okay, so Dr. Kuwabara, may I continue?
Yes.
Shall we continue? Okay. My next question is, in the introduction part, you introduce some approaches to measure the current, like basing on magnetic coupling, then Hall sensor coupling,
Yes.
Hall effect coupling, and electric type coupling, like using resistor.
Yes.
Then what kind of principle you using here for the laminated bar sensor?
Okay, so this my proposed current sensor is similar with Rogowski coil. So how to say, magnetic field detecting.
Magnetic coupling.
Yes, coupling. Yes.
Okay, I see. That's why you use the air core coil,
Yes.
right?
Yes. Yeah. Right.
Okay, then in terms of current sensor, if you use current sensors before, you may know about open loop type or closed loop type. Then the
Yes.
differences between them is the capability of compensation. So, have you ever been thinking about like a compensation for your sensor, like a temperature drift or like a parameter drift compensation?
Actually, that is good question. But I I didn't consider so much. But at least I think this sensor is not there is no thermal effect, because this time the current is so much not big, how to say, small current, just small current flows in the air core coil. So I think
No, the current is very small. It
yes.
is like a air coil transformer, right?
Yes.
Then the problem is when you run the high current in the bus bar,
Yes.
the high current may make the bar hot. Then because the bar is on the top and bottom side,
Yes.
it makes the middle, the middle layer hot.
Yes.
Then it may change some, I don't know. If you do the FEM simulation, you may find out better. But I cannot tell right now.
I see. That is good comment. So maybe I should check the summer drift using FET simulation.
Then because you make a sensor, and I want to add one more comment regarding normalization to make it
Yes.
transducer. You know, sensor is different from transducer because you have to normalize the output to make it from 0 to 3.3 or 0 to 5 volt or 4 to 20 milliamps, you know. Then I think in this case, it is very difficult to normalize the signal because your signal change very quickly and very sharply.
Yes.
The first ranging is about 18 minus 18 volts, but the next one is only 7, and the next one is only minus 2 volts. So have
Uh,
you thought about normalization?
uh, Normalization. No, I didn't consider it that. But that is also a good comment.
Okay. Okay, so I see that someone else have questions. So let's leave the microphone to others. Thank you very much.
Thank you.
Yeah, thank you very much. So, Dr. Cobra, if you still have time, so now we have two questions.
Okay.
Okay. So, Mr. Thum, can you make your question? Hello, Mr. Thum Nguyễn. Can you turn on your mic and make the question? Okay, so
Can you hear
Mr.
me?
Thum, okay. Yeah, please.
Okay. Okay. So I have a really small question regarding this topic. Thank you very much for giving such a very interesting topic related to current sensing. So my question is that when you try to send the current, right, and transfer that to the voltage, um, the voltage really actually really high at the time when the current come from 0 to some high value. But when
Yes.
after the current get over the transient state, the voltage should be really small, right?
Yes.
So is that difficult for you to send the voltage at that time? Because maybe the current voltage at that time may be affected by very small inductor, small resistor. So the same value of the voltage at that time should be this like interfered by some kind of resistor. So how you have an exact measurement of the voltage after the transition time?
Uh, Sorry, I couldn't understand so much your question.
Okay. Let me explain pretty quick again. Okay, so we have pretty high voltage, right? At the time when the current rise up from 0 to some pretty high value.
Okay.
Okay, but after that time, the voltage is pretty small.
Yes, very small.
Because right, so do you have a like some how about the accuracy of your measurement after the transition time?
Okay. So this time, I use the oscilloscope and the resolution. Yes, the resolution is a 12-bit. So that means in this case, we can measure the zero 0.4 millivolt. So in this case, this measurement result is no problem. Enough resolution for measuring the coil voltage.
Okay. Yeah, we can see like after the transition time, like when the it's a slope pretty low, so DIDT pretty small, so the voltage like nearly zero. So
Yes.
what you
Yes.
can read like the fluctuating. So I mean, if you can extract the voltage at that time, it's pretty difficult. I think so. But like, so all your measurement like during that time is correct, right? I mean, it's good. Okay.
Only yes, only this time. Yeah, I can say I can measure. And if yes, yeah, yeah, the small voltage we should consider the resolution because yeah, how to measure the coil voltage is also maybe should be considered more.
Yeah. I think it's really challenging because maybe we have very small like resistor. So during that time, the current flow not only to the inductor but also to the parasitic resistor. So the impact of the resistor
Okay.
and maybe equal to the impact of the inductor during that time. So we don't know. But during change in time, I say okay, the dominant effect should be belong to the inductor, right? But
Yes.
after
Yes.
the change in time, maybe you can consider more about that. I mean, in the later development.
Okay. So let me maybe perhaps I should consider the maybe post-processing method more detailed,
Yeah.
take into the other components.
Yeah. So, but in total, I think like I'm pretty impressed by your achievement, like how you can integrate the current sensor in the bus bar to measure the current directly that way. So, thank you very much.
Thank you. So your question.
Yeah.
Yeah, thank you very much for your question and present. And we have one question now. So if you have time, so
It's okay.
yes. So the question already typing by Mr. Dương Văn Bình, right? So can you make your question? Hello, Mr. Dương Văn Bình. Can you hear and make the question? We cannot hear you even your mic already turned on. Okay, so in the wait time, I can support like talk about his question. His question already typing in the note, and the question is a post-processing method like a PID controller model to force the signal stable in the certain time?
So I couldn't maybe I couldn't hear that. Say it again.
Yes. So also you can see clearly in the note of the Skype. So the question is a post-processing method like a PID controller?
No, this time I just calculated by using no by myself. Didn't use PID controller.
Hello, can you hear me?
Yes.
Yeah.
Sorry. This inconvenient. So actually, my question is, I see the factor K1, K2, K3 for K4 like seem like the factor of BID controller. So how actually my question is how you calculate K1 to K4?
Based on my measurement result and this equation.
Okay.
Yes.
Coefficient equation.
Yes.
And depend on the value of capacity, coil, and resistor on the design on your design.
Yes.
Okay. Thanks.
Thank you.
Yeah, thank you very much. And Dr. Ding, we have one more question. But okay, I think within the 2 minutes is okay. So can you make the short question in 2 minutes?
Okay, sorry for multiple questions because I just realized from the question of Dr. Tum. Then please go back to slide number 20.
20. Okay, wait.
Okay, so here the waveform, you said that you measure using oscilloscope, right?
Yes.
Then I see the ranging, and resonant frequency is very high, 76 megahertz.
Yes.
My question is, how do you discriminate between that ranging of oscilloscope probe or the oscillation of the current sensor? Because when I do the measurement, I also see many ranging, but because it is due to the oscilloscope probe, so how do you discriminate?
This time I measure this voltage without a voltage probe. Just directly connect the coaxial cable to the oscilloscope.
So you don't use the probe?
I don't use probe.
Have you checked before? I mean, double check. You use the coil and the probe to compare the result. So did you?
Sorry.
So have you ever double check between your current measurement method and using oscilloscope probe, the normal probe?
No. But actually, yes, yeah, very maybe 3 years ago or something. I checked firstly I tried to measure the this voltage using the voltage probe, but I also saw some problem like oscillation by the oscilloscope, and if I change the voltage probe, how to say, I change the how to measure without voltage probe.
And the shape also changed, right?
Yeah, also changed. So that's why I think that problem from the voltage probe. So that's why I changed the measurement method.
Okay, so is there any load at the terminal? The load at the terminal of the V coil? You use any resistor or low pass filter or anything?
I didn't use a low pass filter, but between the coil terminal, I put the resistance.
Is this a pure resistance or because in the high frequency, the resistance like the welded wire resistance may have very high inductance.
Yes, I just use a chip resistor.
Okay, so that is just my comment. Please check the parameter of the resistor, the load resistor, at very high frequency, and please confirm that it is a pure resistance.
Okay, I think. Okay.
I think you should use like a shunt resistor.
Yes. Okay. Thank you for your comment.
Okay, so that's all. Sorry for taking too much time.
Yeah, it's okay. Thank you for your many questions.
Hello. Can I make a question? One more.
Okay.
Yeah.
Who's that?
Yes. Can you please introduce yourself first, please?
Yeah. This is Bình, Dương Văn Bình from Ho Chi Minh City University of Technology and Education, Vietnam.
Yes.
Yeah. So again with the page number 12. No, 20. Yeah. That the last question I called how you calculate K1 to K4. So I see on your formula the row of the K1 to K4 is exactly does it determine the time for the signal stability So my question is, do you do any simulation on MATLAB or something software, some software to first determine K1 waveform. So after that, you calculate again to the your resistor or capacitor. I mean, do you get? I mean,
no. Say it again, please.
Here the question is maybe your target, you want to your signal stay stable in the second time on the page 20. You put the signal can stable on 200 nanometer second. So maybe maybe on the certain application, you need to define just only 100 nanometer second. So how you can again calculate the K1, calculate the capacitor, resistor suitable for this target?
But I cannot say 100%. But now I measure this parameter K1 to K4. I measure this parameter using the time domain reflectometry, and that is using the. I can get this parameter based on the step waveform. So in this case, I think that parameter is not changing, even the short time, like to 100 nanosecond. I think.
So you mean you design your model first, and you calculate the parameter capacitor, resistor. After that, you measure and you say the response component, the stable time is you can measure in 200 nanometer second, right?
Yes, and even shorter time, that value is stable.
Okay.
Yeah. So thank you very much for the presents and good question. I think still many people very interesting with your presentation. So if you are very interesting more, and so you can contact to Dr. Kuwabara by Facebook or email. It's shown in this slide.
Okay, and can I say last comment?
Yes.
Okay, so thank you for inviting this webinar, and I'm very appreciated to give me this opportunity to present. And yes, and this is my journal paper and conference paper. If you want to interest in my research, please check it. And if you have any question, you can contact me directly, or you can find my Facebook account and you can contact me. Also, thank you today.
Yeah, thank you, Dr. Kuwabara, very much for your time to take a part into webinar and give the very good presentation today. And hopefully in the future, when you work in company, so we still can talk many times and discuss more.
Yes.
Yeah. Yeah, thank you very much. So I would like to come to the next presenter of the today.
Okay.
So yeah, can you please turn off your share screen? So I will say my screen.